Welcome to this video on complex numbers. This is part of a series of videos on circuit analysis in the frequency domain. Complex numbers extend the real numbers with square root of -1. For instance, the quadratic equation that you see here has no real roots in the real number system because finding the root involves taking the square root of a negative number. There are two notations for expressing the complex numbers. In the rectangular notation, a complex number is expressed as the sum of a real part and an imaginary part. The imaginary part appears as the coefficient of j, which by definition is the square root of -1. In the polar notation, a complex number is expressed as its magnitude and angle. C is the magnitude, theta is the angle, e is the base of natural logarithm, and again, j is the square root of -1. Converting from polar to rectangular form relies on Euler's identity. Two examples of converting complex numbers from polar to rectangular form are provided here. Conversion from the rectangular form to the polar form is based on the geometry of right triangle. The actual angle depends on the sign of a and b. This means that for two complex numbers having real component with absolute value of a and having imaginary component with absolute value of b, but with different signs for a and b in the two complex numbers, the corresponding polar representations have the same magnitude but different angles. This will become clear when we get to know the graphical representation of complex numbers. Two examples of converting complex numbers from rectangular to polar form are provided here. A complex number can be represented graphically on what is called a complex number plane, in which the horizontal axis represents the real values and the vertical axis represents values of the imaginary component of a complex number. The angle is measured counterclockwise from the positive real axis. Alternatively, the angle can be measured clockwise from the positive real axis but with a negative sign for the angle. Here you can see the graphical representation of a complex number whose both real and imaginary components are positive. Either of the notations for representing complex numbers can be used to define a complex number on the complex number plane. If the complex number is given in rectangular form, the values of the real and imaginary components serve as the coordinates for marking the complex number on the complex number plane. On the other hand, if the complex number is given in polar form, the magnitude determines the radial distance from the origin and the angle defines the angle of the radial measurement with respect to the positive real axis. As alluded to when discussing conversion from the rectangular form to the polar form, the quadrant where the angle lies depends on the sign of a and b. The table presented here summarizes this information. Here you can see graphical representation of four different complex numbers. In fact, the absolute value of the real component of all the four complex numbers is the same. Similarly, the absolute value of the imaginary component of all of them is also equal. Only the signs differ, resulting in different angles. A concept usually encountered when dealing with complex numbers is that of the conjugate of a complex number. The conjugate of a complex number is obtained by reversing the sign of the imaginary component of the complex number if it is represented in the rectangular form. If the complex number is given in the polar form, the conjugate is formed by reversing the sign of the angle. As you can see, conjugation reflects the complex number about the real axis. For adding or subtracting complex numbers, they must be in rectangular form. For addition, the real and imaginary parts are added separately. A similar procedure applies for subtraction as well. An example for addition and subtraction of two complex numbers represented in the rectangular form has been provided here. Here is another example in which the two complex numbers are initially in polar form. For multiplication or division, the complex numbers can be in either form, but the polar form is more convenient. For multiplication, if the complex numbers are in rectangular form, multiplication follows the rules of elementary algebra. The only point to note is that j squared is equal to -1. If the complex numbers are in polar form, the magnitudes are multiplied and the angles are added. Here is an example in which two complex numbers are multiplied using both their rectangular and polar representations. For division, if the two numbers are expressed in rectangular form, the numerator and the denominator must be multiplied by the conjugate of the denominator. This reduces the denominator to a real number by which the real and imaginary parts of the resulting numerator are divided. If the complex numbers are in polar form, the magnitude of the dividend is divided by that of the divisor and the angle of the divisor is subtracted from that of the dividend. Here is an example in which two complex numbers are divided using both their rectangular and polar representations. To raise a complex number to an integer power, it is easier to have it in polar form, in which case the magnitude will be raised to the power and the angle will be multiplied by the power. Here is an example in which a complex number is raised to the power of 4 using both its rectangular and polar representations. Here are some useful identities. And some useful identities involving the conjugate of a complex number.